So, good morning. I'll give you a brief report about a project we started last year, and it's very much ongoing. We had the first publication last year, and we are now working on the second one. And it's about looking for objects as close as possible to the bottom of the main sequence. So basically smaller than roughly 20 to 25% of the solar radius and mass, and all the way down to the brown dwarf, and the smaller the better. So the goal is to do good old-fashioned stellar astrophysics at the bottom of the main sequence. We want to understand the radius-mass relation because these objects, as one possible motivation, these objects are very important when they are the primary object in the system, when they are the planet host. But the problem is that you can literally quickly count the number of known objects in this parameter space, as opposed to hundreds of planets with measured radius and mass, and hundreds, if not more, of sun-like stars, FGK stars, with measured radius and mass. So the number is too small, and of course the solution is, like in many other cases, more observations. Let's go out and find more of these stars, and here are some examples. This is the K2 transit or eclipse light curve and the radial velocity curve. This was done with a TRES spectrograph with our colleagues at the CFA. And here are two more. Again, the K2 eclipse light curve and the RV curve. And the bottom two were done with Keck high-res because they're somewhat fainter. We need a bigger aperture. And they were, for some reason, it actually gave us the time. And so these were all published last year, all of them in one paper. And here is their position at the radius mass diagram. You can see we are starting to populate this region in parameter space, and I'm completely ignoring the question, where is the boundary here between stars, brown dwarfs, and planets? Maybe the boundary even should not be plotted in this kind of simple diagram. It can depend on other parameters and beyond. Now, the story I just told you about this really nice scientific motivation, and then we ask, what do we need to do to fulfill or to pursue that goal? Which telescopes do we need to go to? What data we need to get and do the analysis? And we even have some results. That's the story I tell. That's the story I write in proposals. It's not really how it happened. How it happened, it was a planet transit follow-up. And we got some radial velocities for these objects because they were even validated as planets, so they had a K2 number. But of course, immediately after getting the radial velocities, we realized these are not planets, these are small stars. One of them is boundary brown dwarf small star. We did find some planets in this project, but we also find these interesting guys. And this is what happens many times in science. You go after one thing, but along the way, you find something else, and you realize, hey, this is exciting too. I should focus on that as well, and suddenly you have two projects instead of one. But the more the merrier. But there are slight differences in the analysis, or things you need to notice and take care of when analyzing these objects as opposed to star-planet systems. And the most important thing is the mass ratio is roughly 1 to 10. So the mass of the companion M2 is not so much negligible as it is for a star-planet system. More specifically, you cannot remove it from Kepler's third law, or Newton's version of Kepler's third law. More specifically, Adam mentioned earlier, there is a nice way to get the mean stellar density from the transit duration. But that effectively neglects the planet's mass, or more specifically, the planet's mass over the star's volume. So, that can be done for planets, but it cannot be done for small stars. So you need to account for that, and we have done that. On the other hand, the luminosity ratio is negligible because it's a much larger order of magnitude, and that's because, as you know, astronomy 101, luminosity or overall brightness goes down very fast with mass. So here we can derive the radii ratio directly from the transit or eclipse depth. Now, as I said, we are ongoing, and we are working hard, and we have many more objects. I'll show you some of the results we are now trying to put together in the second publication. This is another K2 light curve, and the RV curve that we are now working on completing. As you see, the orbit there is not fully baked. And here is another one, and another orbit which is not fully complete. Both of them are being monitored with Keck high-res because they are somewhat fainter, and we need a large aperture. A few more that we have already finished with TRES because they are brighter, and our colleagues at the CFA are very generous and very smart. So these are 3 objects that we've essentially finished the orbit and now trying to analyze and put together in another publication. And the last result I'll show you is, to me, is very exciting. This is the light curve from KELT. And this part of the project is done with Dan Stevens. So this is the KELT light curve and some follow-up light curves. But the RV curve here is from NRES. And NRES is a new high precision or high resolution spectrograph. It's actually a network of those spectrographs. There are 4 of them mounted on 4 different 1-meter telescopes in 4 different continents, 2 in the north, 2 in the south. And NRES is designed for high precision radial velocity. The pipeline is now being developed and worked on. It's on its way to reach that precision. We used it much earlier on, and you can see here the precision is roughly 1 kilometer, and this is more than enough to measure the orbit of this object. Another interesting feature here is that this is phase folded, but the radial velocities were literally obtained on consecutive nights. So we got an RV each night, so after 10 days or so, we are done, moving on to the next object. And you can do that when you have a fully automated, fully robotic network, global network of telescopes. So you just schedule or submit your observing request online, you go to sleep, and after a few days, you get the data. It's really fun to work like that. And if you have any more questions about NRES, I'll be happy to take them later. I see also Tim Brown is here, who is the person who has the vision behind NRES, is the person who actually built it at LCO. And of course, beyond these results, TESS is coming. It's coming very, very soon. Of course, I'm very biased about this project. It pays my salary. And TESS will give us many, many bright targets for this kind of science that we can then use NRES on a small 1-meter telescope to get the spectroscopy and radial velocity. And I will leave you with, again, the radius mass diagram and the approximate position or rough position of some of the new objects I just showed you that we are still working on and trying to make a global analysis of. And finally, if this sounds interesting to you, and if this sounds fun, and you have some observing resources that you would like to contribute, or even better, theoretical understanding and theoretical analysis, that would be most welcome. I'll be here for the rest of the day. You can also reach me by email. Thank you.
Have some time for questions in the back.
Pierre Max de Keele University. You mentioned that you can get the radius ratio directly from the transit depth. One of the things we worry about when we do a very similar program following up these systems from the WASP project is third light. There's a little discussion of this on poster 105 by Sam Gill. I just wonder, how do you deal with this third light contamination problem?
Yeah, just to make sure everyone are on the same line. Third light means there might be another star somewhere in the system, bounded or not, that is contributing light both to the photometry and spectroscopy and can shake things up. So we try to look for that. It might explain some of the problems we have. We try to also to do high angular resolution imaging to try and see if there is any object really close at the 0.1, 0.2 arc second, close to the object, and look carefully at the spectrum. But overall, it's a problem that we need to account for and see if fitting for that will give us a better agreement between the data, or better agreement with the data and the models. But the bottom line, I don't have any magic solution for that.
Chris Tinney from UNSW Sydney. So there's still quite a lot of scatter in your diagram there.
Yes.
What do you think is more important? Spending more time on individual objects to shrink the uncertainties, or getting more objects?
Well, I would like to do both, but
Assume your resources are limited and you have to make a choice.
my instinct is to put as many objects on this diagram, so once they are there forever. And anyone can go and get more data and get more radio velocities, more photometry, maybe near-infrared spectroscopy or other kind of data set that we are currently not focused on getting. So then the future work can complete that.
Derek Homeyer, Heidelberg State Observatory. Looking at the error bars there, the scatter already looks quite interesting and physical. So have you tried to compare this with different mass radius relations for different metallicities? And do you have a plan to characterize the metallicities of the systems?
So to clarify one thing, the black points and error bars are from the literature, taken as is. And the blue points, we don't really have error bars on them yet because this is work in progress.
Assuming they're the right ones.
We haven't tried to look carefully into the scatter and whether, for example, it depends on metallicity. For example, why is this object down here and this new object, why is it so below the model? This is something we haven't yet focused on, and I do want to focus on that in the near future.
Okay, let's thank Avi one more time.
Thank you.